Okay. Step 4 is to deal with the dot product, in this case multiple dot products because we have multiple integrals, deal with the dot products explicitly. This is one of the most common mistakes that students do when they're trying to apply Gauss's law, is they try to skip steps and do it all at once, and they get into trouble because of that. So it's really worth the time to go through each step explicitly. So in our case, for the curved surface, I forgot to point this out before, but for the curved surface over here, the d vector A is parallel to the electric field, so that's good. So for the curved surface, we have E dot d vector A is equal to E times dA. For the top surface, the d vector A points upwards, but the electric field is always pointing radially outward, and so d vector A is perpendicular to E, so E dot d vector A is equal to 0. And a similar thing happens on the bottom surface. The d vector A points downward on the bottom surface, which again is perpendicular to the electric field. So the top and the bottom have E dot d vector A equals 0. So putting this all together, the integral over the entire surface is equal to just the integral over the curved surface, because due to this E dot dA equaling 0 on top and bottom, those contributions drop out. So that's equal to the integral on the curved surface of simply E times dA. Step 5 is to consider, can I take the electric field out of the integral? So if the electric field is uniform over your remaining surface, in this case meaning the curved surface, is uniform over your surface, you can take it out of the integral. But again, you got to think about that as a separate step, and in particular make sure that that's a separate step from dealing with the dot products. So in this case we can, and so we can say that the electric flux in this case is equal to E times the integral over the curved surface of dA. Step 6 is to evaluate your integral, or perhaps there may be more than one in some case, so integral or integrals, assigning dimensions as needed. So this is something that you're probably not used to doing, but often when you're working a problem, you might need to make up a symbol for something that would be helpful for you, and then perhaps you can figure out what that is later on, the thing that you made the symbol up for. In this case, in order to evaluate this integral, we know that so phi sub E is E times the integral on the curved surface of dA. So that's just going to be E times the area of the cylinder. And we know that the formula for the area of the cylinder is 2 pi r times the length of the cylinder, which I'll just write as a capital L. So r is the radius of the cylinder, and 2 pi r creates the circumference of a circle, and if we slide that down through the length of the cylinder, capital L, that creates the area. But nobody told us a value for capital L. I need to define it. So I'm going to say, all right, now I see I need to know what the length of my cylinder is. I'm going to define a symbol for it. But again, this is just a mathematical cylinder, so that length had better not matter. It had better cancel out somehow when we're trying to find the electric field, which really does matter. Okay. Step 7. So far we've been working on the left side of Gauss's law. Now we're going to start working on the right side. So step 7 is find the net enclosed charge. So in our example, the net enclosed charge is simply the charge per unit length lambda times the length L. And you can see we also need to know the length for this part. Step 8 is to use Gauss's law to find the electric field. So in this case, the left side is the electric flux, which we know is E times 2 pi RL. The right side is the net enclosed charge divided by epsilon naught. The net enclosed charge is lambda times L, and we're dividing that by epsilon naught. And here, the factor of L cancels out, as we knew it had to, because it's not, it's just an aspect of this mathematical cylinder that we made up. It can't have any physical significance. So rearranging this gives us that the electric field due to an infinite rod is equal to lambda divided by epsilon naught times 2 pi r. And if you wanted to express this in terms of the constant k instead, k is just 1 over 4 pi epsilon naught, so this would be 2k lambda over r. So usually this is the form in terms of epsilon naught. Might be more handy, but sometimes you could use this if you wanted to. The final result is somewhat important, especially the fact that it depends on 1 over r. And that's not too surprising, because remember that in a top view, we had the electric field lines going out from our rod like this, and you can see that the farther away from the rod you get, the lower the density of the field lines, and so it makes sense that the field should drop off as 1 over r. So that part is important, but what's way more important is that you understand this procedure. In the next segment, we'll talk about applying Gauss's law to these other classes of symmetry.